In this section, we will look at positional encoding in transformer. As we mentioned in the last section, self-attention is not sensitive to word ordering, and it can be easily seen from this picture. In recurrent neural networks, we encode the sequence from left to right, so each hidden state here would know whether a word occurred recently or in the long past. Now let's look at self-attention. Here, the output is based on pairwise interaction between words, which means that even if we permute the input words, the output wouldn't change. So now the question is word ordering really matter? Well, for NLP tasks, it matters a lot. Let's consider these two sentences. All dogs are smart and some are dumb, versus all dogs are dumb and some are smart. Even though the set of words in these two sentences are exactly the same, the meanings are quite different. So word ordering is important to fully understand the meaning of the sentence. Now, in order to represent the position in the input sequence, the solution in the transformer is to add a positional embedding to the input word embedding. Recall that in self-attention, we have this input sequence matrix X, where each row is a word embedding, and then we project this word embedding matrix into key matrix, query matrices, and so on. Now, we additionally add a positional encoding matrix, which is of the same size as the input sequence matrix. So it's basically element-wise addition. And this position encoding matrix can either be deterministic, which means we hand code some encoding, or learned from the specific task. Okay, how do we encode the positions? There are many different implementations, but today we'll introduce the specific sinusoidal positional embedding, which is used in the original transformer paper. The intuition of using sinusoidal functions comes from binary encoding. So let's consider the simple task of encode the integer from 0 to 7, which represents the indices of the word in the sequence. We want to encode these indices into a binary code. So now let's look at the bits at different positions. So in the leftmost bit, it changes very slowly. So the pattern repeats every 8 bits. So the period is 8 here. Now, if you look at the second bit position, it changes faster. The period is 4, while the rightmost one changes the most frequently. So we have this columns of binary bits whose frequency increases from left to right. And motivated by this, we can come up with a continuous version of this binary encoding implemented by sinusoidal functions. So each columns in this figure corresponds to columns of bits here. So each row would be a position encoding for a specific index or integer. Now the value of each column is given by the sinusoidal functions with increasing frequency. The difference is that here they're continuous values, but here we have the binary values. Okay, so now that we can represent word ordering in our model, the next natural question is, are word ordering really important in downstream tasks? We have argued that they are very important to understand the meaning of the sentences, but maybe most downstream tasks doesn't really require this deep understanding. This is a recent paper which shows that even if you permute the n-grams in the downstream task, so here the orange bar corresponds to random word order and the blue bar corresponds to natural word order. So it's true that the performance goes down a little bit, but not that much, which seems to suggest that word ordering, although useful, is not that useful for current benchmark tasks. So another implication of these results is that our benchmark is not good enough. These tasks are not good proxies for evaluating the understanding capability of a model. And in addition, the results are only in English. Perhaps on a different language, word ordering would be much more important.